Okay, video on polynomial functions. Couple of things here for you to make note of, or some vocabulary things. This word degree. Degree goes with the highest exponent of any term of the polynomial. So the highest exponent of any term would be that fourth power right there. No other term, which are these individual pieces separated by plus and minus signs, no other term has a higher power than 4. So the degree of this polynomial would be 4, so we would call it a quartic polynomial. This would imply that it has possible 4 solutions, whether they're real or imaginary, for the entire polynomial. Or another way to think about it is 4 x-intercepts possible, or it crosses the x-axis up to 4 times. All right, the number of terms are separated here by those plus and minus signs that we talked about. So here, 1, 2, 3, 4, 5 different terms. So this would be a polynomial of 5 terms, or another way would be a 5-term polynomial. I want to model how to analyze one of these polynomial functions. So over here you see the graph, and it looks like we have x-intercepts in those 3 spots, and because we have the arms going in opposite directions, that can lead us to believe that it is an odd function, or something to the first, third, fifth, seventh, ninth, etc. power. An odd degree, odd power function is going to give us arms going in opposite directions. The even powers, kind of like a parabola, would be heading in the same direction. All right, so what I'm going to do is go through different kind of key characteristics of a polynomial function and try to come up with good ways for you to identify those things. So zeros, another name for zeros, are x-intercepts, and it looks like we have 1, 2, 3 of these. So these would all be in the locations of where it crosses the x-axis. So all you have to do is get the coordinates of where those are. If you're doing this on your calculator, you're not limited to them crossing in quote-unquote nice places. You can always do the calculate in your graphing calculator, and it will help you find what those x-intercepts are. But since we're looking at this picture, we have to just do it old school and find what those coordinates are. So let me do that real quick while I put those up. You try to do the same thing. Okay, so here's my 3 x-intercepts, or my 3 zeros. Those would be -3, 0, 1, 0, 4, 0. Notice all of them have a 0 for the y value because we didn't go up and down. They're on the x-axis. All right, so write the factors. That would mean take the zeros and put them into a form of a factor, writing them basically in terms of x. So let me show you what that is, so it could kind of spark maybe some memories from previous classes. Again, what we're doing is we're taking these x values, x equals -3, x equals 1, x equals 4, and we're going backwards to the factored form. So I've laid out for you the process of finding the factors from the zeros, or the x-intercepts. So what I did is I said, okay, the x value is -3. So in order to get this all on the same side and set them equal to 0, because again, that's what we call them, as zeros. So what would it do to make x 0, or make this equal to 0? So I would have to add 3 to both sides to get them all on the same side. X plus 3 equals 0. That's what I mean, make them equal to 0. So that means x plus 3 is the factor that goes with that x-intercept -3, 0. So really quickly, you could probably see I'm doing the opposite of what happens here. So my next factor would be x minus 1 for this, and x minus 4 for this x-intercept. And that's how I would find the zeros really quickly. This discussion will be the talk of extrema. All right, so I've got you some notes right here at the top. So if you want to pause it and write those down somewhere in your notes, that'd probably be a good idea. The maximum and minimum of a function are going to be your extrema. So the highest point and the lowest points of function are going to be your extrema. But One thing to keep in mind is that we do have these things called relative extrema if we don't seem to have an absolute maximum, like the highest point of a function or the lowest point of a function. We do have areas where those things occur in a certain domain of a restricted area of the function. So we're kind of looking the fact that this function continues to go up forever over here, so we're not really going to have a maximum value per se of the whole function, but we do have an area whereas in this portion of the function we do seem to top out and then change directions. Same thing here, we don't seem to have a minimum. Over here it goes down forever, never, never, never because of that arrow, but we do seem to have in this portion of the graph a minimum before it changes directions and starts increasing. So those would fall in the area of relative extrema, and we could come up with what the coordinates for those are. So if you'll just identify those points and write down the coordinates of these points, that's what we're looking for when it comes to the coordinates of the extrema. So in this case over here, we are at -1, 15. And over here to the right, we are at +3, -8. And those would be a relative maximum and this would be a relative minimum, meaning if I just look at that portion of the graph, this is the highest point. If I just look at this portion of the graph, this is the lowest point. So that's what we're talking about with extrema. Talk about increasing and decreasing intervals. So I got you some definitions again if you want to pause and write these things down. But increasing is when the y values are increasing or going up as we move from left to right. So as the x values are getting bigger and heading toward positive infinity. So that means heading toward positive infinity. So starting here and moving this way from left to right, it's what's the graph doing? What are the y values doing? So what you see on the graph is the result, is the y values. All right. So I know this arrow is pointing down and it might make you think that the graph is going down, but the y values, as I move in this direction, the y values are getting higher and higher and higher and higher up until I reach this relative maximum, and then they start to go down. So that's kind of how I want to get you to look at this thing. So when they're asking for increasing intervals, I'm increasing from here all the way until when I get to that x value of -1, because that point seems to be where my graph stops going up and starts to go down. So way back here is negative infinity, and so as I go this way, I get all the way to -1 before I stop going up. So when I write that first increasing interval, it's going to be from negative infinity all the way to -1. Notice that I've got a parenthesis on the negative infinity, but a bracket on the 1. That's not an actual number for negative infinity, so we use that open circle type idea with the parenthesis that I don't actually get somewhere and touch it. But at -1, I do actually get to that number and touch -1, and that's when it changes direction. All right. Then I also see an increasing portion right here. It seems to start going up as I head toward positive infinity. So this is 3 right here. So it seems like at 3, I start to go up again. So my next interval would be from 3 to positive infinity. And again, bracket and parenthesis for the same reasons that we just discussed. All right. That was our increasing intervals. Now here comes our decreasing intervals. That's the y values are decreasing or going down as x heads toward positive infinity. So still moving from left to right. So -1 seemed to be where we started to go down. And as I move from -1 this direction, my y values steadily go down, 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 down until I get to 3. All right, so that is going to be my interval for decreasing or going down. So -1 bracket, because I actually touched that, and then +3 is where the other boundary of going down is, bracket, because I actually touched that. So that would be my decreasing interval from -1 to 3. My y values go down, and then they start to increase after 3. Funny, but we're just now going to start talking about domain and range and the y-intercept, which are, pretty fundamental basic things about a function, and things that we've had a lot of experience with in the past. But we'll go ahead and get those on here as well as a quick refresher for anyone who might need that. Remember, your domain are all the possible x values that are defined on this function. Your range are all the possible y values that are defined on this function. So my domain is how far left to how far right does it go, boundary-wise, and my range is how far down to how far up does it go, boundary-wise. So my domain, notice that I'm continuing to go down and left forever and ever and ever, and up and right forever and ever and ever on this function. So there doesn't seem to be anywhere that I go left or I go right that gets skipped over or I don't ever approach. So our x values, all real numbers are included, so the way that we write that in interval notation would be -infinity to +infinity, open parentheses, because there's no actual number that represents infinity. All right, my range, I seem to go down forever and up forever, and that gives me another one of those -infinity to positive infinities because all y values are covered by this function as well. There is no place that we don't have a y value that gets used. All right, my y-intercept would be where this graph crosses the y-axis. So here's my y-axis there, and there would be where I cross at that point. That's already marked for you on your function, and that would be at the coordinates 0 and +12. 0 for my x value, +12 for my x value. Those would be my range, domain, and y-intercept. Okay, now we're going to talk a little bit about end behavior. If you're not familiar, end behavior is exactly how it sounds. It's how the function behaves as it approaches -infinity and how the function behaves as it approaches +infinity. So way out here to the left, would be as it approaches -infinity, and way out here to the right is what it means when it approaches +infinity. So way out here, as the x values continue to get smaller and smaller and smaller, and I'm moving to my left, the arrows are pointing down. So the end behavior would be defined as x goes toward -infinity, the y values head toward -infinity because it's going down. Sometimes I'll even draw an arrow down to just kind of remind my students that the going to -infinity is going down for my y values. So that might be something to think about. As I'm out here approaching +infinity, so as I continue to move this way to my right, my arrow's pointing up, so my y values are heading up as I continue to move to the right. So as x heads toward +infinity, the y values are increasing and going to +infinity. So that's how we would define end behavior, is way out at the end, where's the graph heading? What's the graph doing? Way out at the ends, in behavior. Keep it simple, don't overthink it. Finally, it asks what type of function is this? And if you notice, there are 3 x-intercepts, so that would be 3 roots, or 3 zeros, or 3 solutions, which would indicate a degree of 3. So up here at the beginning, when we talked about our degree of 3, that would be a cubic function. And so when they ask us what type of function is it, we would say it's a cubic function. Interesting point about what we just said with the type of function. This picture, which seems quite different from our previous example, also has 3 x-intercepts or 3 zeros, and you would think it's also cubic, but look at the arms. They're both pointing in the same direction, which would indicate an even function. So at least one of these is a double root or has a multiplicity of 2, meaning it shows up twice. So this would make it an even powered function. So maybe 4, maybe 6,